Hey there, explorers. Ready to dive into something truly fundamental?
Always up for a challenge.
Excellent. We've got a fascinating set of notes and experiments here, all about matter. The stuff that literally makes up everything around us.
Sounds like we're going deep, deep down to the building blocks of the universe.
You got it. We'll uncover why ice floats, how scents travel, and so much more. But first, the big question. What even is matter anyway?
It's so fundamental we rarely stop to think about it.
Exactly. But our notes here suggest even ancient philosophers were pondering this.
Oh, absolutely. The Indian concept of Panchtattva, with its 5 basic elements, reminds me of ancient Greek ideas about matter.
Right. Air, earth, fire. It's fascinating how different cultures approach this.
Definitely highlights how fundamental these questions are, even across time and cultures. But the real game changer was the idea of matter being made of particles.
Ah, yes, particles. Tiny, tiny things we can't even see.
Imagine thinking the world was just one continuous blob.
Wild, right? So what convinced people about these particles?
Well, simple experiments, actually. Ever dissolved salt or sugar in water?
Sure, who hasn't? Seems like it just disappears.
Right. But it doesn't actually vanish. Those sugar particles are just spreading out among the water particles. That's why the water level doesn't really rise much.
Makes sense. Those sugar particles must be incredibly small to fit in those spaces.
Incredibly. Another mind-blowing demo is the potassium permanganate one. A few tiny crystals can color a huge amount of water.
Oh yeah, that vivid purple spreading out. So cool.
It shows how many tiny particles must be in those crystals, dividing into smaller and smaller ones.
And those particles are constantly in motion, right?
Well,
Like how we can smell things from a distance.
exactly. Those coffee particles are mixing with the air, reaching your nose. It's a whole invisible world of movement.
That's incredible. But okay, we've got these particles making up everything. What about those different states of matter? Solid, liquid, gas, we all kind of know them. But
Yeah.
how do particles explain those differences?
It's all about how those particles are arranged and how much they're moving and how strongly they're attracted to each other.
Okay, so solids, they seem pretty rigid.
Right. Picture a group of people packed tightly together, barely able to move. That's a solid. Those particles are locked in a specific arrangement, strong forces holding them together.
Like a super organized party where nobody dances.
Exactly. That's why solids have a definite shape and volume. You can't easily compress a book, right?
Right, makes sense. So then liquids, they flow and stuff.
Now imagine those party people can move a bit, but they're still close together. Liquids. The particles can flow past each other, taking the shape of their container.
Okay, so they're mingling but not going wild.
Exactly. And they still have a definite volume. A liter of water is always a liter, no matter the container.
Got it. So gases, they must be the wild ones at the party.
You got it. Imagine those party goers running around freely, filling the whole space. Gas particles are far apart, weak forces between them, bouncing all over the place.
Ah, so that's why we can compress gases like in a balloon. They've got space to squeeze into.
Exactly. And they expand to fill any space they're given. No definite shape or R volume.
Okay, so before we go further, let's nail down those definitions. Solid is.
Definite shape and volume. Particles are super tight, strong forces at play.
And liquid.
Takes the shape of its container, but keeps a constant volume. Particles move more freely, but still kind of close together.
And last but not least, gases.
No definite shape, no definite volume. Those particles are far apart and moving randomly.
Perfect. Now, I'm really curious how matter shifts between these states. We see ice melt into water, water boil.
Yeah.
But what's happening with those particles? And what role do temperature and pressure play?
Ah, the transformations. That's where things get even more fascinating. But we've got a lot to uncover there. You were asking about how matter transforms between those states. It all comes down to energy and how it affects those tiny particles we've been discussing.
Or we see ice melt, puddles evaporate. But what's the science behind it?
Temperature plays a key role. Adding heat gives those particles more energy, making them move faster.
Makes sense. More energy, more movement.
Think about a solid, particles packed tight, just vibrating. Add heat, they start wiggling more, and eventually...
They break free.
Exactly. They overcome the forces holding them together and start flowing past each other. That's melting. Solid to liquid.
Okay, melting. So, like our party analogy, they're allowed to dance now.
You got it. Now, let's crank up the music for boiling. Keep adding heat. Those liquid particles move even faster.
They get wild.
And they gain enough energy to completely break free, escaping into the air as a gas.
Boiling. A dramatic exit from the party. So melting and boiling points are like specific temperatures for these changes, right?
Precisely. Each substance has its own. Water, for example, melts at 0 degrees Celsius and boils at 100.
Oh, right, at normal pressure.
Exactly. Those temperatures tell us about the strength of the forces between those water molecules.
Speaking of pressure, how does that affect things? We talked about compressing gases.
Pressure is crucial, especially for gases. Increasing pressure forces those particles closer, strengthening the forces between them.
Like squeezing those partygoers into a tiny room.
Exactly. They're more likely to interact, even bond, under pressure. So squeezing a gas can make it easier to become a liquid.
Makes sense. And does pressure affect the boiling point of liquids too?
Absolutely. Ever tried boiling water in the mountains?
I have. It boils faster, but food takes forever to cook.
That's because there's less atmospheric pressure pushing down.
Oh, interesting. So less pressure, lower boiling point.
Right. Those water molecules escape more easily at higher altitudes. Now, what about those weird transitions like sublimation?
Sublimation.
Yeah.
Dry ice comes to mind. Skipping the liquid part completely, solid to gas.
Fascinating, right? Like those partygoers teleporting out. Dry ice is solid carbon dioxide, and at normal pressure, it goes straight to gas.
So no liquid stage at all.
Yep. Same with those mothballs. They're made of camphor, which also sublimates.
So those solid particles are just becoming gas directly.
Exactly. It's all about vapor pressure. Some substances, like dry ice, have high vapor pressure even as solids.
Meaning?
Their particles are super eager to escape into the gas phase, even below their melting point.
Wow. No waiting in line for them. And deposition is the opposite, right?
Yep.
Gas to solid directly.
You got it! Like those partygoers suddenly freezing in place. Think of frost forming. Water vapor becomes ice crystals directly.
No liquid water in between.
Straight from gas to solid. We've got all these ways matter changes states. Melting, boiling, sublimation, deposition.
Yeah, it's all about those particles gaining or losing energy, breaking free or bonding.
Right. But what about the energy involved in those changes? That's where latent heat comes in.
Latent heat, we skimmed over that earlier.
It's the energy needed to change a substance's state without changing its temperature.
How does that work?
Think of melting ice. You add heat, but the temperature stays at 0 degrees Celsius until all the ice is melted.
So where's that heat going?
It's breaking those bonds between the water molecules, giving them the freedom to move as a liquid.
Ah, so the energy is used for the change itself, not for raising the temperature.
Exactly. It's like an energy investment for rearranging those particles.
An energy investment. And there are different types of latent heat, right? Like for melting and boiling.
You nailed it. Latent heat of fusion for solid to liquid, latent heat of vaporization for liquid to gas.
Okay, fusion for melting, vaporization for boiling.
Think about boiling water. It stays at 100 degrees, but you need to keep adding heat.
To keep it boiling.
That's the latent heat of vaporization, breaking those bonds so water molecules can escape as steam.
Okay, that makes sense. So during a phase change, the temperature stays the same, but energy is still being used.
It's like a hidden energy exchange behind the scenes. Which leads us to another everyday phenomenon, evaporation.
Evaporation. Puddles drying, clothes on a line. But how's that different from boiling? Both involve turning into a gas, right?
Great question. Both involve liquid to gas, but boiling happens throughout the liquid when it hits its boiling point, with bubbles and all. Evaporation is more chill, just at the surface.
So not the whole liquid, just some escape artists at the surface.
Exactly. Even below boiling point, some surface particles have enough energy to break free.
And what affects how fast the liquid evaporates? We know temperature matters. A hot puddle dries faster.
You're right. Higher temperature means more surface particles have the energy to escape.
Makes sense. But what else?
Surface area matters. Think of spreading laundry to dry. More surface exposed to air, faster evaporation.
More escape routes. What about wind?
Wind helps a lot. It carries away the water vapor, making space for more to escape.
Like clearing the way for those escape artists. And humidity. I know clothes dry slower on humid days.
Humidity is how much moisture is already in the air. High humidity means less room for more to evaporate.
Like trying to fit more people into a packed room?
Exactly. So temperature, surface area, wind, humidity all play a role. Now, here's a question. Why does evaporation have a cooling effect? Great observation. Remember those energetic particles escaping? They take some of the liquid's heat energy with them.
They're stealing energy as they leave.
Exactly. The remaining liquid and anything in contact with it loses energy, hence the cooling.
That's why sweating cools us down.
Yeah.
It's amazing we've covered so much. Melting, boiling, sublimation, deposition, now evaporation.
It's all connected. But before we wrap up, we should highlight the unique properties of each state of matter, why they matter in the grand scheme of things.
Right. We focus on the changes, but what makes each state special? Let's explore those unique properties and their impact before we finish up this deep dive. We're back and ready to wrap up our deep dive into the fascinating world of matter. We've seen how those tiny particles behave in solids, liquids, and gases, how they move and shake, and how temperature and pressure can cause those dramatic changes of state.
Absolutely. From melting ice to boiling water, even that wild sublimation thing with dry ice, it's all about energy and those incredible particles.
Right. And we explored how evaporation works, those sneaky particles escaping from the surface and taking heat with them. But before we call it a day, we could talk about what makes each state of matter special, right?
You hit the nail on the head. We've been so busy with those transitions, we haven't really appreciated what makes each state unique.
So let's start with solids. What are those key properties that make them, well, solid?
Well, as we discussed, solids have a definite shape and volume. Their particles are all packed in tight, a very specific arrangement, like a well-behaved, motionless crowd.
Right. No dancing allowed at this party.
Exactly. And that tight structure gives solids their strength and stability. Think of steel beams in a building, or those massive rock formations in mountains.
So their strength comes from that fixed arrangement of particles. Makes sense. Now liquids.
Yeah.
They're all about flowing and adapting, right?
Exactly. Liquid particles are still close, but they have more freedom to move around, sliding past each other. So they take the shape of their container.
Like they're going with the flow, but still keeping their own volume.
Right, and this fluidity is essential for so much. The water cycle, for instance. Rain, rivers, oceans, all that movement. And blood circulating in our bodies carrying those vital things.
Without liquids, our world would be very different indeed. And speaking of different, let's talk about gases. They're the free spirits, right?
The rebels of the matter world. Gas particles are far apart, zipping around at high speeds, hardly any forces between them.
Sounds like a chaotic party.
You got it. And because of that lack of structure, they expand to fill any container they're in. Makes them incredibly versatile and super important for life.
Think of the air we breathe. A mix of gases surrounding us, filling our lungs. And there's so many other vital roles gases play, right?
Oh, absolutely. Oxygen for burning things, carbon dioxide for plants, essential stuff. And on a cosmic scale, gases make up stars, those giant clouds of gas and dust, even the vast spaces between galaxies.
Wow, it's amazing to think about. Solids with their strength, liquids with their adaptability, and gases with their expansiveness. They all have their own unique roles in this incredible universe.
Absolutely. And when we understand these properties, it's like getting a whole new perspective on the world. It makes you appreciate the complexity and beauty, even in the most ordinary things.
This has been an incredible journey. We went from defining matter to exploring its hidden world of particles, uncovered the secrets of state changes, and even figured out why evaporation feels cool.
It's been a fantastic exploration, a reminder that curiosity and the wonders of nature never get old.
What's the one big takeaway you hope our listeners will remember from our deep dive?
That matter is the building block of everything. Understanding its properties and how it behaves helps us appreciate how this incredible universe works. From the tiniest atom to the largest star, it's all connected.
A truly inspiring thought. I hope our listeners are feeling excited to keep exploring the world with a newfound appreciation for the matter that makes up everything they see and touch.
I have no doubt they are.
Thanks for joining us on this deep dive into the world of matter. Until next time, keep those minds curious and those questions coming.